I don't know what was more disturbing. Sons in second grade, they get this division thing, worksheet, reducing fractions, or it was just, all the answers would be integers in theory. And they had 0 divided by 0 on this worksheet for second graders. And you know, my son, being the child of 2 math science people, knew what the answer knew that the answer was not definable. But the teacher marked it wrong because the enter key said 0. I'm going, what? Is it more disturbing that she couldn't think for herself, or the fact that the answer key was wrong? Anyway, I digress. They cancel each other out, so it's just 3.143 if you want. Or if you're a fan of units, it's centimeters per centimeter. But don't suddenly multiply them, or don't just make one go away. All right, so that's the spiel on the importance of units and sort of how you deal with them. But let's take it one step further. Let's see, which equation do I want to use? Let's sort of combine units with significant digits here. So here is an equation that you will see later on in the course. This is what I will refer to later as one of the cake formulas, cake standing for constant acceleration kinematic equations. This is chapter 2 stuff. This is displacement. We'll derive this equation later, but just need an equation for right now. Displacement, velocity, time. The subscript I here, this is actually initial velocity. This is acceleration and time. So if the displacement, let's actually solve for that. So my initial velocity is, why don't we say 40.0 meters per second. Time is 3.00 seconds. Acceleration, negative 4.21 meters per second squared. And we already have time. So basically, taking significant figures into account, what is the displacement? So we just sort of do a plug and chug here. So I have 40 times 3, this is VI times t, plus 1/2 times acceleration, negative 4.21, times 3 squared. And let's do it in parts. This one I can do. This is 120. And I could stick in the extra plus 3 zeros there, but how many significant digits should this be based on what I multiplied? Why 2?
Because 40, oh no, 3, because of the trailing zeros on the end of the decimal on both of them.
So these both have 3 significant digits. This is a trailing 0 to the right of the decimal, therefore that is significant. 4 is significant, and so that makes the middle one significant. Here, they're both trailing zeros to the right of the decimal, so they are significant. And so that has 3. So this is 3 significant figures. So that 0 is significant there, which I'm indicating by putting a decimal point. Plus, over here, if you work that whole math thing out, first give me just the full number, ignoring significant digits, and then we'll talk about where the significance ends.
got negative 18.945.
All right. See if anyone else backed you up on that.
That's what I got.
Yes, I'm here.
All right. Seems to be a groundswell. Where does this significance end?
Should just be three significant figures again, correct? Because the negative 4.21 has 3, and the 3 has 3, so it should end around 0.9.
So you're going there.
Yeah.
What about the 1/2? Thanks for not revealing the 1/2 already, for people to think about it, which is what I was hoping. So you were about to say something when I cut you off, sorry.
I think it would, because of the half, it would. That would just be. Okay, you got me there.
All right, let's take a look from a slightly different point of view. Or, sorry, let me do a dramatic pause to see if someone else wants to chime in before we do the different point of view. All right. What is the relationship between the diameter and the radius of a circle?
The radius is half the diameter.
Okay. Yeah, trying to gauge the class, I wasn't quite sure whether just the language of radius and diameter were strange to some people or people were just being shy. We are all going to make plenty of mistakes in this class. So if you have a fear of showing that you are making a mistake in front of other people, the sooner you sort of get past that, the better I think it's going to be for everybody. So just chime in. Take chances, make mistakes, get messy. That's what the frizz would do. All right. And by the way, when I make a reference to the frizz, do I have anyone who understands the reference? Got one. Wow.
Y'all didn't watch the Magic School Bus?
Oh, no.
All right. So if my diameter is 5.64 meters, what is my radius? So, does multiplying by 1/2, or dividing by 2, which is the same thing, mean that this should actually just be 3 written here? Does multiplying by 1/2 change the precision of our measurement?
No.
I hope not. So, how do we deal with the 1/2 here? How do we deal with the 1/2 there in terms of significant digits? Well, this has infinite significance. We're not going to write out 0.500 and keep writing zeros on forever because, well, then you never do anything else. But numbers like this that are stuck up front, this is not rounded off. It is exactly 1/2. And so, and this was a rule I didn't throw in when we talked about significant figures, but exact numbers have infinite significance. So multiplying by 1/2 does not change, since that number 1/2 is exact, does not change the number of significant figures in our answer. So over here, going back to, I think Ian was the one, this would be 3 significant figures because that 1/2 does not change. So it's 3, 3, and infinity. So you go with the least. Now in terms of adding now, I know that 9 is basically the precision of that. So we have 120 minus 18.945. Again, as we do our math, we keep all the numbers there. It's only at the end that we care. So I'm going to go for a different color here. This is here just for the fact that I'm subtracting. 1, 9. So 5, 5, 0, 1, 0, 1. This 120 was significant to that 0 right there. This 18.945 was significant to there. So our final answer is significant to here, because that is the least precise of our significant digits. So if we cared about significant digits, the answer is 101. Now we have to deal with units. Questions about the 101 before we do units?
So on a lab, you would want 101?
On the first lab, yes. After that, go wild. Right, so units. So we have this 40. So now I'm just going to do the same thing, except I'm going to just put it down in units. That 40 was meters per second times seconds plus, well, that's unitless. And this was meters per second squared times seconds squared. So what's meters per second times second?
Would it just be meters? Because the seconds cancel?
Yeah. So if I have a meter per second times a second, I can stick anything over 1. And then when multiplying fractions, common factors can be canceled out, and I'm left with meters. I guess in math class I'd write meters over 1, but just meters. And over here, what would that reduce to?
Meters.
Because this is a second squared, canceling out with that second squared, and what I'm left with is meters. And so that's 120 meters and minus 18.945 meters, and so we end up with meters in the end. If you have 120 apples and you take 18.945 apples away, how many apples are you left with? Except, we confuse some people by calling them meters instead of apples. Questions to hear? All right, so a little bit about base units, unit systems. For the most part, we will do most of our, at least final presentation of answers in terms of what are called SI units. And for what does SI stand? Yeah. Okay. International standard, and the reason why it's not IS is because it's French. Standard international. For those with better French accents, now would be a chance to say it so that people aren't corrupted by the way I said it. I guess the corruption will continue. All right, so we'll mainly use SI units. These are metric. These are a form of metric units, sometimes called the NKS system, as opposed to the CGS system. And these are just standards. So when you have derived units, a Newton is a derived unit, which we'll get to in chapter 4. That is based upon these units right here, not this set of units. And then there's US customary. Because we're stubborn, or we dare to be different, or take your pick. But don't forget, the Metric Conversion Act of 1973 is going to put us all in metric. You can see it. There's a road sign in Tennessee when you're how many miles it is to Chattanooga, I think, when you're going from Knoxville, where it tells you how far it is in kilometers as well. Metric Conversion Act of 1973 in action. All right, so length. Oh, and then I'll stick generic over here, the ones that I know. All right, so length. That's what the M stands for right there, meters. Meters is the standard unit. In the CGS system, the C stands for centimeters. So if you were taking this course 40 years ago, you probably would have done a lot of your measurements in terms of centimeters instead of meters. US customary. Again, even though inches is a US customary unit, it is not part of the standard. The standard is the foot. And generic is just a capital L. This is leading to something known as dimensional analysis. Mass. That's what the K stands for. Kilograms is the international standard. The old standard, the things that things should always be put in, that's what the G stands for, grams. And here's the one that I'm going to try to keep alive as long as possible. What is the US customary unit for mass? It is not the pound.
Ounces?
No. Occasionally there's a student who's heard this.
LBS.
The slug. I've never actually seen the slug being used. There's this thing called pound mass that I'm still not 100% sure what that is. But
How much does a slug weigh?
depends on where you are. So my weight, I'm more than that, but I'm just dealing with the number. So I'm a little bit more than 200 pounds. You know, let's be slightly more realistic, 215 pounds. That is my weight. If I divide by 32.2, that would tell me the number of slugs that I am. So actually, how many slugs am I? 6 point something?
6.67701.
6.67701?
Mm-hmm.
Let's round off. All right. So my mass is about 6.7 slugs. So that is pounds, and this is feet per second squared. And so you get slugs. And then my mass is roughly 100 kilograms in the MKS system. So that gives you some sense of slugs to kilograms at least. You want to take a shot for the generic for mass?
Yeah.
Capital M more specifically. Fortunately, not a lowercase m because that you use too much as it is. Time. That's what the S is. Seconds. Hey, the same thing there. Hey, it's the same thing there. And generic?
Lowercase t.
Actually, uppercase. This is a generic unit. The lowercase t would stand for the variable time as opposed to the unit of time. And I'll put this into practice probably today, but if not, then Thursday. So those are the big three right there. There are some other ones. Temperature. Spell that right? Well, use your imagination. So the standard for temperature, you might think metric is degrees Celsius. Actually, that's not the standard. There's an easy translation back and forth, but anyone happen to know what the standard temperature is for unit for a metric?
Joules?
There's actually a relationship to joules, but it's not joules specifically.
Kelvin.
Kelvin?
It is indeed Kelvin. It is not degrees Kelvin, it's just Kelvin. And that's the same in both systems there. And then in US Customary, again, another one of those units that I've never actually seen in practice, but it does exist. I guess another unit to keep alive for as long as I can, the Rankin. I feel bad for the guy. He was doing a lot of work, I think about the same time Kelvin was doing, and then he gets assigned the unit that's not used. And then the generic for temperature, since capital T was already taken, theta typically is the, if in doubt, go to the Greek alphabet. What begins with a T? They could have gone, I guess, for tau. Those are basically the 4. There's 7 of them, but those are basically the 4 that we use in this course. What am I forgetting? Amount is one of them. Current, amount of substance, and oh, of course, luminous intensity. I guess amount potentially we hit in this class. I don't think we do, but amount. Flashback to chemistry. They generally talk about amount of a substance. I was hoping at least one of you had had chemistry before.
Was it moles?
It is. Good memories?
Fine.
And the abbreviation for mole, they got really clever with this one. They just dropped the E. And that's the same across. I'm not going to worry about that over here. When you're doing dimensional analysis, which is what we're heading towards, amount is just a number. There's no real... The units are problem specific. There are 11 people in this room. We could express that in number of moles if we wanted to. All right, so dimensional analysis. So let's go back to the equation that I had written up here before. And again, hoping to get a darker pen there. Yeah. So all we're going to do is we're not going to worry about the numbers. This is just a very crude check to see does this equation make any sense whatsoever. It's just a first check. And so this is displacement, which deals with I start at this point, I end up at that point, how far away and in what direction. We're not going to worry about the direction, but this in essence, the magnitude of this is just a length. So this would be L. So all I'm doing is I'm putting in the units for this equation right here. VI, that's a speed. Think of miles per hour, feet per second, meters per second. It is some distance divided by some time. So this is a length divided by time. If I use the lowercase t here, then suddenly we have 2 lowercase t's, which means something different. One is generic time, and the other one is unit of time. So that's why we go with capital T. Time, that's just t. 1/2 has no units, so I'm not worrying about that. Acceleration, that is something like meters per second squared or feet per second squared. Parsecs per year, hour. But it is just generically, it is some length over some time squared. Those are the generic units for acceleration, and time is time squared. Now the left-hand side and the right-hand side should match in the end. And then you do it step by step. Order of operations, you do the multiplication first before you do the addition. T's would cancel out, I'm left with L. Over here, t squared cancels out with that t squared, I'm left with L. When I'm adding or subtracting, I better have the same units. You combine apples, you combine oranges, but you don't combine apples and oranges. And so I have some number of L's plus some number of L's is going to give me some number of L's. That works. This is dimensionally sound. If I had left the 1/2 off, it's still dimensionally sound. It's not a correct equation anymore, but it's still sound dimensionally. So, but this is just a brief, crude check. And there's a video I did for dimensional analysis where I actually pulled an equation from a published article and showed how that equation does not work. If they had just done dimensional analysis, they wouldn't have put in the mistake. It was a philosophy paper, so I guess they didn't know a lot of math people checking it over. Looking at dimensional analysis, there is an equation here. Force is equal to mass times acceleration. I consider it personally as the most important equation in all of physics. We will get to it in chapter 4. Dimensionally, I have a mass here. Generic unit for mass, capital M. Acceleration. Generically, we just did that one. It's some length over time squared. So the units of force should be, well, some mass unit times some length unit over some time squared unit. Therefore, if this equation is true, then the units of force, and I will represent that by putting in brackets there, the units of force is some mass times some length over time squared. So that means that a kilogram meter per second squared is a unit of force. A gram centimeter per second squared is a unit of force. A slug parsec over hour times year, it's an awkward unit, but it is still legitimately a unit of force because it is a mass, a length, and 2 times. I don't think that's a unit you will ever use. Notice that when our units over here, we have kilogram meters per second squared. These are all SI units. Kilograms, meters, and seconds. Force happens so often, they said, well, since I don't feel like writing kilogram meters per second squared all the time, so let's make up something. And so they defined this. 3 dashes there, indicating that it is by definition. That is a Newton. A Newton is a SI unit for force. It's not one of the base units, it's not one of the building blocks, but it's known as a derived unit. The gram centimeter per second squared. Hey, all of those are in the CGS system. That also has a defined unit. That is the dyne. Some of our force scales over there will have dynes written on them. That's what it's just a unit of force. Just using the older standard. Yeah, we got time. We'll assume it's actually accurate to 3 decimal places there, or to 3 significant figures. My weight's about 980 newtons. How many dynes is that? We're using this as a segue into unit conversion. 980 Newton, well, a Newton is a kilogram meter per second squared, so let's just write down kilogram meter per second squared. And that's a decimal point there. Let's worry about significant figures here. So when I do conversions, I need to convert each of the units. Well, first off, I have to get kilograms into grams, because again, a dyne is a gram centimeter per second squared. So how many grams in a kilogram or kilograms in a gram? 1,000 what into what?
1,000 grams equal a kilogram.
All right. So what I'm going to do is I'm going to multiply this by 1. Because the math people tell me as long as I multiply by 1, I got the same number. So I'm multiplying, this is a multiplication here, times 1, which means, well, the math people again tell me as long as the numerator and denominator are the same thing, but not 0, it's equal to 1. Flashback to centimeters per centimeter. I have kilograms up here and I want to get rid of them, so I put kilograms down here. 1 kilogram is equal to 1,000 grams. Numerator and denominator are equal. Therefore, I'm multiplying by 1. Meters. Meters into centimeters or centimeters into meters.
Centimeters, centimeters.
Right, so how many centimeters in a meter?
170 centimeters.
All right. Again, I want to get rid of meters, so I need to, since it's on top, it cancels out with something on the bottom. You're going to claim in that's 100 centimeters per meter. How confident are you in that?
Very confident.
All right. And so meters cancels out with meters. So now I'm left with grams centimeters per second squared. So we actually could do one more conversion, depends on how pedantic you want to be. Gram centimeters per second squared per dyne. Just to get it in dynes. All right, so we do the multiplication out. So we have 9, 8, 0, 1, 2, 1, 2, 3. So that's the math up part of it. So 98 million dynes is my weight. Where's the significance? How many significant digits in my final answer?
2.
Why 2?
Because there's no decimal at the end.
Except the number of significance depends on what I started with and work my way across. The way it's written right now, it would be 2, but the question is, do I need to display this slightly differently? How many significant digits should this be? Perhaps that's better wording.
Is it 3?
Why 3?
Because we started off with 980. Wait, was that a...
That's a decimal point.
Okay.
Yeah, so that has 3 significant digits. But how many significant